Hello students, welcome back to the lecture of this course. In the last 3 lectures I was discussing about the principles of NMR spectroscopy, and I started discussing about how to get the structure of a molecule using NMR spectroscopy. I will continue with that, and then I will again go to 2D NMR spectroscopy, and I will let you know what is the potential of 2D NMR spectroscopy and how it can be used for elucidation of structure. In the last lecture I discussed how 4 different features of NMR can be used to get information about a compound structure. Those 4 features are number of signals, position of signals, intensity of signals, and spin splitting of signals. I will give you one example. So, let us look at 1D NMR of this compound NS2, CH2, CH2, and CH3 twice. As you can see, there are 2 proton attached to nitrogen, 2 proton attached to carbon, 2 protons attached to this carbon, and your 6 protons attached to these 2 carbons. These 6 protons are equivalent because they have same environment. These 2 protons are equivalent. Similarly, these 2 protons are equivalent and these 2 protons are equivalent. And so, there is 4 different groups, one consisting of this 6 proton, another consisting of these 2 protons, the third one consists of these 2 protons, and fourth one consists of these 2 protons. So, there are 4 different kind of protons, and so number of signals is going to be 4. That is what we expect in 1D NMR, and this is your 1D NMR, and you can see there are 4 different peaks, 4 different peaks. So, let us go and understand how to assign this. The intensity of signals, if you look at this is the ratio of intensity of signals, and you can see the ratio is 1:1:3, 3:1. 1:1:3:1, and if you remember here there is 2 protons here. So, total is 4, 2 protons here, 6, and then 3 here, 3 here. So, 6 plus 6, 12 protons. 12 protons, and intensity, if you sum this is equal to 2 plus 3 plus 1 is 6. So, let us divide this by 2. So, 12 divided by 6 is equal to 2. So, one basically if you look at the equivalent hydrogens, so we need to multiply this by 2. If I multiply this by 2, then I get the first group consists of 2 protons, the second group consists of 2 protons, the third group consists of 6 protons, and fourth group consists of 2 protons. The way we got is simply we multiply this by 2. So, first thing is that when you get 1D NMR, you look at the intensity and then you look at your compound and see how many protons are there. Now, you sum all the intensity ratio, and if suppose this comes to be 6 and there are 12 protons, it means that each the intensity ratio corresponds to 2 protons, So, if intensity ratio is 1, that corresponds to 2 proton. If intensity ratio is 3, then that corresponds to 6 protons. So, that is how we can get information from intensity observed in case of proton NMR, and when you do that it is quite easy to give the assignments. This has your intensity 3, means there should be 6 protons which are equivalent, and if you look at the structure, only these protons are equivalent and their number are 6. So, from the intensity itself you can assign this peak. From intensity itself you can assign this peak. You can also look at the position of signal. So, for that you need to look at the electronegativity, and if you look at the electronegativity, then this should come at a smaller chemical shift, this should come at your highest chemical shift, because this is attached to electronegative atom. These protons are attached to NCH3 twice group, which is less electronegative than NH2 group, and so these protons will come at higher position, higher chemical shift position, whereas these protons will come at lower chemical shift position. So, now you can also assign BC here, and D we have already assigned, and this will be A based on your position or based on the chemical shift value. There are another thing which you can look at, that is splitting. In this B and C, you see these are 2 protons here which will couple with the 2 protons here. So, they will be split into 3. So, both B and C protons are expected to split into 3, and here again this is CH3 and they are not coupled to each other, they are not coupled to any nearby proton, and so you expect a single peak. So, this is the way you can assign the peaks of the 1D NMR, 13C carbon nuclei is also NMR active, and so we can also look at 13C NMR, and here you can see that there are 3 different kind of carbon. One is B, C and D, these are CH3, and so they are equivalent to each other since both has same environment. So, you expect 3 peaks, and that is what you see here. There are 3 different peaks, 62.76, 45.68 and 39.68. Now, if we want to assign these protons, if we want to know which of this carbon gives you this peak, we need to do another experiment called DEPT experiment. DEPT experiment can be of 2 types, DEPT 90 and DEPT 135. DEPT stands for distortionless enhancement by polarization transfer, and it is a preferred method for determining number of protons attached to carbons. There are 2 different kind of DEPT, DEPT 90, DEPT 135. This 90, 135 is basically your proton pulse angle. A proton pulse angle is set at 90 degree, it is known as DEPT 90, whereas if proton pulse angle is set to be 135 degree, then it is known as DEPT 135. In DEPT 90 only CH shows, so you will not see any peak due to CH2 or CH3, whereas in DEPT 135 CH2s are phased down, whereas CH and CH3 are phased up. So, you will get positive signal and negative signal depending on kind of carbon. Okay. Here when I say kind of carbon, I means carbon is attached to how many protons. So, this is example of DEPT 90 and DEPT 135 of this molecule. And now you can see that if we look at the CH, I have only one CH group, only one CH group. So, I will get only one peak in DEPT 90, only one peak in DEPT 90. But if I go to DEPT 135, then you look here, this is CH3, this is CH3 and this is CH3 and this is CH2 and this is CH2. So, you will get peak due to your all three CH, CH2, CH3, CH2 peak will be down. So, these two peaks are due to CH2. And if you look at this CH2, there are two different kind of CH2, this is CH2 and this is CH2. So, you got two different peak for CH2. CH will come at higher chemical shift in comparison to CH3, and this is your CH peak, this is your CH peak and this is your CH3 peak. This is your CH3 peak, and since there are three different kind of CH3, and so you got three different CH3 peak, three different CH3 peak. CH is, there is one H here also. So, there is two CH group, and so you are getting two peaks corresponding to CH, and you have a 3 CH3 group, and so you got three peaks for CH3 and two peaks for CH2. Based on that, you can assign different carbons. Now, come back to the same compound which we are dealing with, and if I do DEPT 135, I will get peak of CH and CH3 up and CH2 down. So, you see there are two CH2 here belonging to these two CH2, where is CH3 this, and this has only one peak. So, 45.68 is now assigned to CH3 group, now assigned to CH3 group. So, carbon, these carbons has chemical shift 45.68. This is the way you can assign proton, you can assign carbon. So, but still that may not be enough, and for assignment and structure calculation you may need to use 2D NMR, and they are very useful when protons are overlapping, when protons are overlapping. So, two protons having same chemical shift can be assigned if their correlation with nearby proton is different or nearby protons is different, and then you can look at the proton-proton correlation to proton-proton correlation to distinguish between two different protons. Two protons with same chemical shift can be assigned if their correlation with carbon to which they are attached is different, and in that you can look at your heteroatom correlation, means carbon and proton correlation. So, the two different kind of 2D NMR experiment you can think of, one which correlates proton with proton and another which correlates proton with carbon or proton with nitrogen. So, 1D NMR we have already seen. In 2D NMR there will be two dimension, one dimension can be proton, the other dimension can be proton or carbon. If you are particularly doing with organic compound, then people try to look at the correlation between proton and carbon. There are sometimes if you go to more complex molecule, for example your proteins, in that case people also look at 3D NMR and 4D NMR. So, basically you are trying to differentiate between different proton based on their correlation with heteroatoms and other protons in the system. So, most common 2D NMR experiments are COSY, where proton and proton are correlated, and then there is experiment called head core, in which carbon and proton is correlated. HMQC is better version of head core, and again this is related to CH correlation. HSQC, CH correlation. HMBC, here the carbon and hydrogen are correlated, which are separate by 2 to 3 bonds. Then the next 2D experiment is NOGI. NOGI looks at the nearby proximity of 2 protons, nearby proximity of 2 protons. So, 2D NMR spectroscopy is important because it gives you an idea about who is talking to whom. The first simplest one is proton-proton COSY. It tells you how and which protons are coupled to one another. It is very useful when peaks are overlapping in proton NMR and you are unable to calculate coupling constant, or when there are a lot of similar coupling constant. There will be 2 different kind of peaks in 2D NMR. One is your diagonal peak and another is cross peaks. What you are looking at is cross peaks. Cross peaks are coupled to each other. When there is coupling, then we will see a cross peak. And one of the important variation of this spectroscopy method is DQF-COSY, which is double quantum filtered COSY. Same information, but it is more cleaner. Let us look at this molecule. Now, you can see there is a correlation between this proton and this proton, and that is what you can see. Now, as I told, in COSY there is a diagonal peak and there are cross peaks. Diagonal peaks are not that much useful. What is useful is cross peaks, because that tells you about that this proton is talking to which proton, which next proton. So, here is the 5 cross peaks, because there are 5 different atoms. So, this is one, this is the second, and this is the third, and then your gamma, fourth one. Now, you look at their correlation. So, now you see NH is basically, if you look at this, NH is correlated to H alpha, and that is how you can assign it. Now, H alpha is correlated to H beta. So, you can see there is a cross peak here, there is cross peak here, and they are correlated to 2 different resonances, and the way we can get it is draw a vertical line, draw a horizontal line, and it coincides with this peak and this peak. It means these 2 peaks are correlated. So, H alpha and H beta protons are correlated, and then H beta is correlated to 2 gamma, 2 different gamma, and that is your CH3 groups. So, correlation between different protons can be seen through COSY. Then comes the DQF, which is double quantum filtered COSY. Now, let us understand about what we mean by double quantum or multiple quantum filters. So, if there are 2 spins, they can be in alpha alpha state, beta alpha state, alpha beta state, and beta beta state. Alpha means you are talking about up spin, beta means you are talking about down spin. So, if both are up, then you have a alpha alpha, and if both are down, then this is beta beta. If I spin is down and S spin is up, then you have beta alpha. When I spin is up and S spin is down, then you have alpha beta. And now if you go from alpha to alpha beta, this this transition corresponds to change in spin to delta S is equal to 1. So, it is basically you are going from, so this is half and here is half, here a half and this is minus half. So, you are going from half to minus half. So, delta S is minus half, so delta S is minus 1. And if delta S is minus 1 or plus 1, then basically you have a single quantum transition. So, if total spin change is 1, then you have single quantum transition, and that you can see with this transition and this transition. So, A1, A2, X1, X2, the total spin change is 1. If you look at the DQ is basically this one, and here you see you are going from alpha to beta beta, and here the total spin change is 2, and that transition is called double quantum transition. If you go from beta alpha to alpha beta or alpha beta to beta alpha, the spin change is 0, and that kind of transition is known as zero quantum transition. So, if we look at normal COSY, it will look like this, but if you go to double quantum filter COSY, it will look like this. So, these two are positive peaks and these two are your negative peak. These two are negative peaks and they give much cleaner spectra, and so nowadays your DQF-COSY is carried out. So, this is COSY, which shows the correlation between protons that are coupled to each other. Then HSQC, as we discussed before, that it shows correlation between carbon and protons that are bonded directly to one another. So, this side is your carbon chemical shift, whereas this side is proton chemical shift, and you are looking at the correlation. So, this side is, you see, this is your proton NMR spectrum and this side is your carbon NMR spectrum. Now, again come back to this compound which we were discussing. This has already been assigned, and that is what we did previously. So, this is your proton NMR, and this has been assigned to, if you take A, B, C, D different kind of protons, and this is your assigned spectrum, 1D spectrum. Then if you go and take COSY, you will get this kind of COSY, this is DQF-COSY, and now you can see the correlation. So, if you look at this cross peak and put horizontal lines and vertical lines. So, now you know that this one is correlated to, these two peaks are correlated, this belongs to C, this belongs to B. So, B and C are correlated, and that is expected because this B and this C are nearby to each other, and so their protons are coupled, and so you can get the corresponding peaks in COSY. So, COSY gives you an idea about the protons which are near to each other, and here you see D is only your correlated to D, there is no cross peaks, and so there is no protons which are coupled to the protons labeled by D. Now, let us look at its correlation. So, you can see that there are 3 different kind of carbons. So, you got 3 different peak, and now you can correlate this carbon is basically correlated with this carbon is basically attached to this proton. This carbon is attached to this proton and this carbon is attached to this proton. So now you can, this is for D. So carbon chemical shift for this proton D carbon carbon chemical shift of D carbon is 45 ppm, and carbon chemical shift for C carbon is your around 62.5, whereas carbon chemical shift of B carbon is 40 ppm. So this is the way you can assign all the peaks. Now you can also carry out HMBC, and this is particularly useful if your compound is quite big. It shows correlation between protons and carbon that are 2 to 3 bonds apart, So this side again there is a proton NMR spectrum, and the y axis is your carbon NMR spectrum. Now look at here correlation. Now you see this is your HMBC for this compound, your B, C, D. Now you can see that B is correlated to, if you look at 1, 2, so here you see this C is correlated to B, since it is one bond apart, and then you can see that look at this B is correlated to C, and C is correlated to D, and now you see here this D is correlated to not only C, it is also correlated to your D. So this D is correlated, okay, this is D is correlated to C, and D is correlated to this one also. And now B is correlated to D, B is also correlated to D, and you see this is 1 bond, 2 bond, 3 bond apart. Now what I will do, that I will give you one structure, and we will discuss about how to get all the resonance and structure from the NMR spectrum. So this is a compound which has molecular formula C10H18O, and this is the your structure of this compound, which is ipsenol. Now let us see how we can assign it. So first thing we need to know how many aliphatic carbons. So it has 2 methyl group here, right, and this is CH2 group, and this is CH2 group, there is a CH group, and this is CH2 group, all right, and there is H here. So it has 2 methyl group, 1 CH, let us see CH, this one is CH, 2 CH2, this CH2, this CH2 group, this is aliphatic carbon. Oh, so this is one CH group, sorry, this is one CH group, this is not aliphatic. Then one CHO group, so this is CHO, so OH group, so this is one group. 2 double bond CH2 group, so CH2, CH2, and 1 double bond CH, 1 double bond CH, and 1 double bond C, so 1 double bond C. So these are all the, this is 1 double bond C, which is not attached to any proton. So this is the way this structure is. So if you count hydrogen atom, you have 3 here, okay, 3, 3, 6, oh, there is one proton here also, 1 proton here also. So, this is your 3, 4, 3, 7, 2, 9, 10, 2, 12, 14, 15 and 2, 17 and 1, 18. So, there is 18 hydrogen, but protons attached to carbon is 17. If you neglect this, then proton attached to carbon is 17. In all 17 hydrogen, 2 is as a methyl group, 1 is CH. So, this is not CH, this one is CH, 2 CH2, these two are CH2 group, 1 CHO. So, this is 1 CHO, this is 1 CHO, and 4 olefinic carbons, 2 CH2 and 1 double bond CH, 1 double bond CH and 1 double bond C. So, this is thing. So, here we have looked at how many protons which are attached to carbon. The one missing might be attached to heteroatom, and so this is your heteroatom OH, and that is how you can count about 18H. Now, look at its proton spectrum. This is your proton spectrum of this compound. Now, if you go by intensity ratio, this will correspond to 1H, this will correspond to 4H, and since they are at higher chemical shift, so they can be assigned as olefinic 1 CH double bond, 2 CH 2 double bond. So, this can be assigned, and from this you can again see that this 4 has same environment and this one has different environment, and so this can be assigned to CH2 double bond and this will be assigned to CH double. Okay. So, again by intensity ratio you can assign this to 1H, and this chemical shift region is your H attached to CO group, H attached to CO group, and then you have the intensity ratio is here quite high, it is like 6H. So, it means you have 2 methyl triplet here. So, this can be assigned now, and there are 6H which will come from one from CH 2 into 2 4 from CH2 and one from OH. Now, it is a bit difficult to assign here. So, what we will do that we will go for 2D experiments. So, these are aliphatic region. So, let us go and look at the COSY of this structure. Now, these are peaks which are on diagonal, and now I know that this is for CH3. So, let us see the things which we have already assigned. This is for methyl, this is CHO double bond CH2 double bond CH. Now, let us see if I relate this is related to this peak, okay. This is related to this peak which is due to methyl group is related to this one, and so this O, this red circle corresponds to the CH group which is attached to 2 methyl group. So, now I am able to assign this peak. Now, let us go and look at. So, this one, this red circle is now correlated to this peaks, and that corresponds to this triangle, and if you go and look at the structure, basically this CH is attached to this CH2, and now we know that this CH2 basically corresponds to this triangle. So, now this CH2 is also assigned, this CH2 is also assigned. Now, you see this is correlated to these two peaks is also correlated to CHO. So, that is what is correlated, and so it is now quite easy to assign peaks which was difficult to assign by 1D NMR. So, till now we have already assigned. Now, look at this and see that this H is coupled to which proton, So, you see this is coupled to two different kind of proton. This proton we have already seen that there is a coupling between these two protons, but there is also coupling with this two peaks, and that correspond to these two peaks. So, if you look at this, so this is basically coupled to this CH2 group. So, now the chemical shift of this is also assigned, or these protons are also assigned. Now, let us go where these two protons are correlated. These two protons are correlated to this, and this is a very weak peak. So, if you go and see the structure, this is also related to double bond CH2, and so you can see this CH2 is correlated to double bond CH2. This CHO is correlated to your this double bond CH2, and this is a weak peak because it is 2 bond apart. This CH2 and this CH2 are 2 bond apart, and so a very weak peak will be seen. And if you remember, this structure also has this thing. So, this CH2 is also correlated to this CH, and the way you can see is this, you remember this CH2. So, they are also attached to this weaker peak, and that corresponds to your this CH. Okay, this corresponds to this CH2. So, this is also correlated to this by this one, and if you go here, the CH2 which is here, and this CH2 is correlated to this CH2 is also correlated to this CH. So, this CH is correlated to CH2, and so this CH protons are shown here, this CH protons are shown here. So, there is a correlation between CH2, which is this CH2 and this CH, and that can be seen here, that can be seen from here. And this is how we correlate different protons, and we assign all the peaks. So, 2D NMR is used for more complex organic molecules, since a lot of chemical shifts are overlapping, particularly in the aliphatic region. It is difficult to assign the protons which are attached to similar kind of carbon, and in that case, based on proton they cannot be assigned, and so it is better to go for COSY kind of a spectrum. So, here I show you some more COSY spectrum of some more molecules. So, here is your molecule C double bond C, COOH, and this is H, and here is Cl, and the second carbon is attached with H and Cl. So, in COSY you will look at the correlation between HA and HX, and you can see here that here is the correlation between HA and HX. So, you will see two peaks which are cross peaks, one both showing the correlation between HA and HX. Now, if you look at this compound, which is ortho nitroaniline, in this case there are 4 different kind of proton which is attached to carbon, and there is one more which is attached to your NS2 group. And if you look at here, then your HA, HC, HB, HB, HD, HB and NS2. So, the lowest one is NS2, and since others are attached to carbon, double bond carbon. So, they have higher chemical shift value, HA has highest chemical shift value because it is nearby to an electron withdrawing group, and that affects HA and HC more because they are an ortho and para position, and so you get HA, SC. Now, you can look at the correlation. HA is correlated to HB, Now, SC is correlated to HC. If you look at SC, it is correlated to these 2 peaks, and that is your HB and HD, So, HC is correlated to HB and HD. Now, you see this HD is correlated to HC, HD is correlated to HC, and this HB is correlated to SC and HA, HC and HB is correlated to HA, HC. So, based on that, if you have a confusion, there is a bit confusion between HD and HB, and so you can assign the HB and SD peaks looking at the COSY spectrum. Now, we will look at the head core. This side is your proton spectrum. So, your y axis is proton and x axis is your carbon spectrum. Now, we can also assign the carbon. So, we know that this corresponds to CH. So, carbon of this proton can be assigned, and that corresponds to around 138 ppm. Now, this CH2, here you see this side is your. So, now you can assign these protons also, and they have your carbon chemical shift around these values. Now, CHO, you see this, well, around this carbon is going to have chemical shift, carbon chemical shift around your 75 ppm. These 2 protons is correlated to this carbon, which comes at 40 ppm, and again this proton comes is correlated to these carbons, which comes around 30 ppm, and then these 2 protons are correlated to this carbon, which comes around your 48 or 50 ppm, and this methyl protons is correlated to carbon, which is at 20 ppm. So, we have seen how COSY is used to assign the different protons, and now we have seen how head core can be used to assign your carbon attached to those particular protons. Similarly, in place of a head core, you can use your HMQC or HSQC to look at the correlation between carbon and proton, and this is the way you can assign the different NMR signals, NMR can also be used as to see the structure of biomolecule, for example, proteins. They are basically fingerprints of the structure of the molecule. Here we show you the HSQC where 15N has been correlated with proton for a protein, and you can see that there are several peaks, and that basically corresponds to your amide nitrogen and proton correlation. So, first thing is how to assign it. The assignment is done using your 3D experiments, for example, HNCA, where the correlation between a proton attached to nitrogen and C alpha is seen. Basically, here you are looking at the correlation between proton attached to nitrogen and C alpha. So, here what has been done is there is on x axis there is proton, and y axis there is carbon, and on z axis you are taking nitrogen, and that is why it is known as 3D NMR method. And for one value of N, basically one value of nitrogen chemical shift, you can look at how proton and carbon is correlated. So, proton will be correlated with 13 C alpha of ith amino acid and 13 C alpha of I minus 1 amino acid. So, proton is correlated to C alpha of ith amino acid and your C alpha of I minus 1 amino acid. Now, what you do is you try to correlate each of this 15N plane with other planes and try to find out where there is your correlation, and so you can find out you can assign the backbone resonances. Now, the way you do is now you take all the planes, all the different planes which differ in 15N chemical shift, and now try to look at that which plane coincides with the plane where C alpha of preceding residues is correlated with C alpha of the residue of ith residue. Now, look at here, this big circle is given for ith, the correlation between proton and C alpha of the same species, whereas this smaller circle is given for correlation between proton, amide proton of ith residue and C alpha of preceding residue, So, if you look at here, this is 2 peaks, and what does this tells you? This is your for ith residue, and this is for I minus 1 residue. The smaller circle is matched, a smaller circle of ith residue is matched with bigger circle of I minus 1 residue, I minus 1 residue, and that is how you see this one is matched to bigger, a smaller is matched to bigger, a smaller is matched to bigger, and this is the way you know how you can assign the back bond, how you can assign the back bond. Similarly, you can do for HNCO experiment, and once you assign all the peaks in HSQC, now you can go and determine just based on chemical shift what will be the secondary structure, what will be the secondary structure, that is done by comparing 13C alpha chemical shift and 13C beta chemical shift of the given protein and their deviation from the chemical shift of the amino acid when they are in random coil. And your 13C alpha, 13C beta chemical shift, based on chemical shift also you can assign which amino acid it may belong to, and that is going to help you when you are assigning the peaks based on HNCA or HNCO experiments. And these are the few facts which has been seen, that chemical shift of 13C beta varies between 15 to 24 for alanine. This C beta peak will be absent for in the glycine. Serine, it varies from 58 to 67, and these are the few things which you can use during the assignment. Now, once you have assigned all the peaks corresponding to your protons in a protein, you go for NOE, and NOE gives you distance between two protons, and as distance are used for construction of a house, similarly here distance constraint is used to fold the protein using your computational software. So, in the first you generate a simple random coil consisting of all the amino acids, and then you put constraint, distance constraint and dihedral constraint, and that is used to fold the protein, and that is how NMR structure of a protein is generated. The different NOE distance restraint can be 3D15N edited NOESY, 3D 13C edited NOESY, 4D 13C edited NOESY, 3D 15N 13C edited NOESY, and 3D 15N 15N edited NOESY. We can also use the dihedral information obtained from 3 bond H alpha coupling constant. I have already told you about the Karplus equation, which is this, and that can be used to get this dihedral angle theta, and that can also be used as a constraint when you are solving NMR structure. The third constraint comes from residual dipolar coupling measurement, where dipolar coupling is basically dependent on theta, and where theta is the angle of NH vector with the external magnetic field, and these angles can be used for the structure calculation, and the way we measure dipolar coupling is to put it inside a bicell, where now the protein will be partially, in that case protein will be partially aligned with the magnetic field, and that is how you can get the information about theta. This is the same how dipolar coupling can be related to the different angles, and using those angle information we can basically get more accurate NMR structure. So, this is the way in which dipolar coupling measurement is done. This is your decoupled spectra. If we take coupled, so you can get in phase and anti phase. This is your J value, and if the you take coupled spectra in alignment medium, your difference will be equal to J plus D. Difference will be equal to J plus D. So, once you take the spectra in absence of alignment medium, you get the value of J. In the alignment media, you get the value of J plus D. So, you can know what is the dipolar coupling value, and that is how you can get another constant which can be used to get a much better quality structure. The second thing which you can do using HSQC is that you can also get the information about interaction. So, here there is overlay of HSQC of cytochrome C with or without cytochrome B5. So, what you are trying to look at is how cytochrome C interacts with cytochrome B5, and there is a overlap of HSQC peak, and you can see that a lot of peaks are quite overlapping with each other. You see here quite overlapping with each other, but there are certain peaks which is moving, for example, T89, L68, G77, and this information where peaks are moving can give you an idea at which part of cytochrome C is interacting with cytochrome B5. So, using that chemical shift deviation, you can measure the binding constant, and this is your one of the typical peak which we used to get the binding constant of cytochrome C with cytochrome B5. So, once you know that this molecules, this interface is involved in binding with another protein, then you can just put that into software. Here HADOC has been used. HADOC is a software which utilizes that information about the interface to do the docking, and if you incorporate those information, you will get a much better complex structure. So, NMR can also be used to look at the binding site or getting a complex structure. So, thank you very much, and I hope that I have given a flavor of how to use NMR in structure calculation of protein and organic molecule. The scope of NMR is quite vast. It is difficult to talk about every aspect in just 4 lectures, but I hope that this is good enough background for you to go and look at NMR quite closely. So, thank you very much.